You're building an engineer, not assembling a toy collection. That's the distinction most parents miss when they're standing in the aisle staring at rows of robot kits. And it's the difference between a scattered pile of gadgets and a kid who can genuinely design, build, and program autonomous systems by the time they're 15. I'm Chloe Miller, and I've watched my own nephews go from playing with screen-free logic bots at age 5 to programming PID loops for solar tracking robots as teenagers. You're listening to the STEM Lab podcast. Quick heads up, everything you're about to hear was researched, verified, and written by a real human author. That's me, but the voice you're hearing is AI generated. Just wanted to be upfront about that. If you've been listening for a while, thank you. Seriously. It's listeners like you who make this show possible and keep us motivated to put out helpful content week after week. If you're brand new here, welcome aboard. We release new episodes every Monday, Wednesday, and Friday, covering practical STEM learning strategies, product breakdowns, and real-world project ideas. Now, here's what we're diving into today. The robotics learning path for kids isn't a grab bag of whatever looks cool on the shelf. It's a carefully sequenced climb from tactile understanding to competition-grade autonomy, and the difference between a structured path and a random approach is profound. This is your complete map of that journey: what hardware to acquire when, which programming languages unlock which capabilities, and how each stage prepares your child for the next. Whether you're starting with a 4-year-old who needs physical cause and effect or a teenager eyeing FIRST Robotics, you'll know exactly what belongs in your home STEM lab at every phase. Let's start at the foundation stage, ages 4 through 7. This is about physical logic and cause-effect mastery. Before code comes comprehension. Your child needs to internalize that actions have predictable consequences, that pushing a sequence of buttons in a specific order produces a specific outcome. This is where the robotics learning path begins, and it's entirely screen-free for good reason. Screen-free directional robots like Cubetto or Code and Go Robot Mouse teach sequencing without syntax. These run on AA batteries or rechargeable packs, no internet connectivity required, built from durable ABS plastic that survives drops and spills. They build the mental model for loops and conditionals before introducing abstract symbols. Marble-run logic builders, things like Gravitrax or Turing Tumble, develop spatial reasoning and debugging instincts. You're watching your child physically trace cause and effect, adjusting ramp angles and gate sequences, no consumables, no subscriptions, just reusable components and a lifetime of reconfiguration. Gear and pulley construction sets from brands like Connects Education or Learning Resources introduce mechanical advantage and force transmission. These aren't robots yet, but they're teaching the physics that makes robots move. No power required, and you can expect 5+ years of hard use if you keep them out of direct sunlight. Magnetic circuit blocks, Snap Circuits Jr. or Little Bits, bridge the gap between mechanical and electronic thinking. Your child sees electricity flow, lights activate, motors spin. These kits are modular, and you'll expand them later. They require 9-volt batteries or USB power. The Snap Circuits Jr. SC100 is the foundational set. Most kids outgrow within 2 years, so plan for expansion packs. Check the link below to see the current price. Pre-programmed animatronic kits, like Tom's and Cosmos Kids' FIRST Robot Engineer, deliver immediate gratification. No coding, just assembly. They're motivating, but they're a dead end if you stop here. Use them to hook interest, not as the destination. They run on AA batteries, and motor life is around 50 hours of runtime before gearbox wear becomes noticeable. Now let's talk about the block-based programming stage, ages 7 through 10. This is visual coding and sensor integration. Here's where the robotics learning path shifts from physical manipulation to logical abstraction. Block-based languages like Scratch and Blockly let children construct programs visually, dragging conditional statements and loops into sequence without wrestling syntax errors. You'll see their spatial logic from the foundation stage translate directly into algorithmic thinking. Bluetooth-enabled block robots like Sphero Indie or Botley 2.0 pair tactile play with screen-based programming. These use rechargeable lithium-ion batteries that give you 60 to 90 minutes per charge, Bluetooth 5.0 for tablet or laptop connectivity, and they work with iOS, Android, Windows, and Mac. The Sphero Indie Student Kit frustrates some kids because Bluetooth pairing occasionally drops mid-session. Keep devices within 3 meters and avoid crowded Wi-Fi environments. Check the link below to see the current price. LEGO Education Spike Essential bridges construction and code. Your child builds mechanically sound robots, then programs them using Scratch-based software. Expandability is superb. Motors, sensors, and structural elements are cross-compatible with Technic and Mindstorm's lines. The rechargeable hub uses USB-C and gives you about 2 hours of runtime. It is cloud-dependent, meaning lessons and firmware updates require internet access. Arduino-compatible block coding boards like MBOT or MakeBlock Cody Rocky introduce industry-standard microcontrollers disguised as friendly toys. These run MBlock, which is a Scratch 3.0 fork, but they can transition to Arduino C++ later. The MakeBlock MBot Neo uses ESP32 microcontrollers and supports Wi-Fi and Bluetooth, but the proprietary battery connector means you'll need to order replacements from MakeBlock, which is a frustrating lock-in. Check the link below to see the current price. Camera vision robots like Q by Wonder Workshop teach sensor fusion and computer vision basics. Kids program responses to visual input, following colored objects, recognizing faces. The skill outcome here is understanding how robots perceive their environment, not just how they move through it. Requires a tablet running iOS 13 or higher or Android 8 or higher, and you'll need occasional app updates. Multi-terrain rovers like Vex Go or Elegoo Tumbler force kids to think about mechanical design trade-offs, treads for traction versus wheels for speed, weight distribution, center of gravity. These kits prepare students for Vex IQ competition formats. They run on 6 AA batteries or rechargeable packs. The aluminum chassis holds up through years of competition practice, and they're fully expandable with over 200 compatible parts. Moving on to the text-based programming stage, ages 10 through 14, this is Python, C++, and real engineering tools. Block-based programming hits a ceiling around age 10. Your child needs real syntax, real debugging, real version control. This is the inflection point where the robotics learning path for kids becomes the robotics learning path, period. The same tools professionals use. Python programmable robots, things like Raspberry Pi-based rovers or Pimoroni STS Pi, teach the language-dominating machine learning and automation. By the end of this stage, your child should write functions, import libraries, and debug runtime errors independently. These require a separate Raspberry Pi 4 with at least 4 GB of RAM, a micro SD card that's 32 GB or larger, and a 5-volt, 3-amp USB-C power supply. They run Raspberry Pi OS, which is Debian Linux, and they're offline capable once libraries are installed. Arduino robotics kits expose kids to C++ and microcontroller programming, the backbone of industrial automation and IoT devices. The Allego Smart Robot Car Kit v4.0 is a solid example. These kits don't hold your hand. Documentation assumes you understand basic electronics, but once your child builds and codes their first obstacle-avoiding rover, they've crossed into legitimate embedded systems engineering. Arduino IDE runs on Windows, Mac, and Linux, fully offline after initial setup. The Allego kit's ultrasonic sensor mount is flimsy, so reinforce it with a dab of hot glue or reprint it if you have access to FDM 3D printing capabilities. Check the link below to see the current price. LEGO Mindstorm's Robot Inventor straddles block and text programming. Kids start with visual Scratch-like code, then graduate to MicroPython. Expandability is unmatched. Hundreds of third-party sensors, pneumatics, custom 3D printed parts. The rechargeable hub uses USB-C and gives you about 150 minutes of runtime. It's cloud-dependent for initial setup and periodic firmware updates. Motors are rated for over 10,000 hours, but gear teeth strip if you over-torque builds. ROS-compatible educational platforms like Turtlebot 3 Burger or Yaboom Robot Car introduce Robot Operating System, the industry framework for autonomous systems research. This is graduate-level territory compressed into a teen-accessible package. The skill outcome is understanding distributed computing, SLAM, which is simultaneous localization and mapping, and sensor fusion, requires Ubuntu Linux, significant computational resources, like a laptop with 8 gigabytes of RAM or more, and patience, not for casual hobbyists. Custom Arduino plus 3D printed chassis builds represent the apex of this stage. Your child designs the robot body in Tinkercad or Fusion 360, prints it on a home 3D printer, sources motors and sensors individually, and writes firmware from scratch. No kit, no instructions, pure engineering. Budget around $150 to $200 for electronics. Filament costs are negligible. Now we reach the competition and specialization stage, ages 13 and up. This is team robotics and advanced autonomy. The robotics learning path for kids culminates here, designing, building, and programming robots that compete against other teams under time pressure and strict rule sets. This is where your child discovers whether they love mechanical design, software architecture, project management, or all three. FIRST Robotics competition kit blocks like AndyMark, KitBot, or Rev Robotics Starter Bundle teach the specific tool chains FRC teams use: CAD and SolidWorks or Onshape, programming in Java or C++, pneumatics, PID control loops, rigorous safety standards. They aren't bedroom projects. They require dedicated workshop space, power tools, and adult supervision. Skills translate directly to mechanical engineering and software development careers. VEX Robotics competition systems scale down the complexity without dumbing down the challenge. Teens design and build robots entirely from VEX metal structural components, program in VEX code, which can be C++ or blocks, and compete in regional and national tournaments. Expandability is unlimited within the VEX ecosystem. They use rechargeable 12-volt lithium batteries with about 90 minutes of runtime. Your child will destroy and rebuild the same robot a dozen times per season. That's the point. Autonomous racing platforms like F1 or Donkey Car focus on perception, planning, and control algorithms. These robots use cameras and LiDAR to navigate tracks at high speed without human input. Programming languages are Python for high-level logic, C++ for real-time performance. The skill outcome is understanding the same autonomy stack used in self-driving cars. Requires significant compute power, a Jetson Nano at minimum, and costs $300 to $600 to build. Not beginner-friendly, but transformative for kids serious about robotics careers. Underwater ROV competitions like Mate ROV or Sea Perch teach unique engineering constraints: buoyancy, waterproofing, tether management, thruster control. These robots operate where humans can't see or reach. The Blue Robotics Blue Rove 2 electronics kit is the semi-professional standard, running Arduino sub firmware, which is open source. Power comes from 14.8-volt lithium batteries and waterproof enclosures. Skills gained include fluid dynamics, sealing techniques, remote teleoperation, disciplines distinct from land-based robotics. Check the link below to see the current price. Custom specialization projects like solar tracking robots, hydroponic automation systems, wildlife monitoring rovers let your teen apply robotics to personal passions. I've built solar-powered rovers that automatically adjust panel angles throughout the day, combining renewable energy principles with PID control. These projects often integrate Arduino programming, CAD design, 3D printing, and environmental science. No kit exists. Your child defines the problem, researches solutions, and iterates. Machine learning integration, things like TensorFlow Lite models on Raspberry Pi or Edge Impulse for microcontrollers, teaches robots to learn from data rather than follow rigid rules. Your teen collects training datasets, trains models, and deploys them on resource-constrained hardware. The skill outcome is understanding the intersection of AI and robotics. Before you go, here's your final checklist to print and keep with your home STEM lab inventory. Foundation stage, ages 4 through 7, screen-free robots, gear sets, circuit blocks, all battery-powered, no subscriptions. Block programming stage, ages 7 through 10, Bluetooth robots, Spike Essential, MBOT, rechargeable, app-dependent, expandable. Text programming stage, ages 10 through 14, Raspberry Pi Rovers, Arduino kits, Mindstorms, requires a laptop, offline capable, open ecosystem. Competition stage, ages 13 and up, FRC or VRC kits, autonomous racers, ROVs, team-based, workshop space needed, career track skills. Verify compatibility before buying. Check OS requirements like Windows, Mac, Linux. Check IDE support for Arduino, Python, ROS. Check the expansion ecosystem. Plan for obsolescence. Kits your child outgrows in under 2 years are stepping stones, not investments. Budget accordingly. Prioritize open platforms. Proprietary batteries, closed software, and single vendor ecosystems lock you in. Arduino, Raspberry Pi, and Vex are expandable for life. Let me answer a few common questions. What age should my child start the robotics learning path for kids? Your child can begin tactile robotics learning as early as age 4 with screen-free sequencing robots like Cubetto or Code and Go Robot Mouse, which build cause and effect understanding and directional logic without requiring reading or coding skills. These foundational tools prepare them for block-based programming around age 7. Do all robotics kits require ongoing subscriptions or consumable purchases? Most quality robotics kits do not require subscriptions, but cloud-dependent platforms like Lego Spike and Mindstorms need periodic internet access for firmware updates and lesson downloads. Avoid kits with proprietary batteries or closed ecosystems and prioritize open-source platforms like Arduino and Raspberry Pi that never lock you into recurring costs. How do I know when my child is ready to transition from block-based to text-based robot programming? Your child is ready to transition from block-based to text-based programming when they consistently build complex multi-conditional programs with nested loops and variables in Scratch or MBlock, demonstrate patience for debugging logical errors, and express frustration with the limitations of visual interfaces. That's typically around ages 10 through 12, depending on prior experience. Here's the thing. The robotics learning path for kids isn't a ladder you climb once. It's a scaffold you build piece by piece, each platform supporting the next. I've seen 7-year-olds debug Scratch code with more rigor than some junior developers, and I've watched teenagers present autonomous rover designs at science fairs that would impress engineering professors. The difference wasn't innate genius, it was sequential skill building with the right tools at the right time. Start where your child is, not where you wish they were. Invest in open platforms that grow with them. And when they inevitably dismantle their third robot to build something you don't recognize, trust the process. That's exactly what engineers do. You're not buying toys. You're provisioning a decade-long apprenticeship in systems thinking, and the world desperately needs what they're learning to build. That wraps up this episode of the STEM Lab podcast. Thanks for spending part of your day with me. New episodes drop every Monday, Wednesday, and Friday, so there's always something fresh coming your way. If you found this helpful, I'd be incredibly grateful if you'd leave us a 5-star rating and write a quick review. I know it sounds like a small thing, but it genuinely helps other parents and educators discover the show when they're searching for resources like this. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. See you next time.